Welcome to this explainer. I'm so glad you're joining us today. This explainer is brought to you by Forge College. Now, if you've been writing Rust, you already know the drill, right? The compiler rules are famously strict. Honestly, I like to think of the Rust borrow checker as this highly meticulous, maybe slightly grumpy patent inspector. You know, the kind of guy who demands absolute perfection before giving your engineering blueprint that official stamp of approval. One little mistake, one overlapping memory claim, and boom, rejected. So today, we're going to learn exactly how to draft those blueprints perfectly so you pass inspection every single time. Let's get to it.
Here's our engineering agenda for today. We'll start with the engineering sandbox, then move right into the art of borrowing, taking full ownership, splitting mutable borrows, and finally, testing your inventions. Okay, part 1, the engineering sandbox, from theory to blueprint.
First off, a huge congratulations on surviving that last super intense lesson on ownership and low-level memory management in Rust. Seriously, it's a tough one. You've got the theory down pat, moves, borrows, lifetimes, stack versus heap, the whole shebang. But now it's time to actually build things. On the left here, we've got all that abstract theory. It's great for textbooks, but on the right is what our strict patent inspector actually wants to see on your desk today: concrete application. We need to take those abstract ideas and translate them into code that compiles cleanly, keeps unsafe blocks to an absolute minimum, and most importantly, keeps that borrow checker totally happy. Moving right along to part 2, the art of borrowing. Look, but definitely don't touch.
Let's dive straight into our very first blueprint. This is all about how to read an account's data buffer without accidentally, taking it home or making these massively expensive copies. The absolute key here is the zero copy or borrowed view. Basically, this just means reading an account buffer safely by purely referencing the original data. No copying at all, no allocating fresh memory on the heap. Our patent inspector absolutely loves this, and frankly, so should you, because it is the pinnacle of memory efficiency. When you're working in a highly constrained environment like a Solana program, you really don't want to waste your precious compute resources building a duplicate machine. You just want to look directly at the original blueprint, safely and cheaply.
Take a look at the actual code signature for this pattern. We've got our parse account function, and it takes a buffer, buff, which is just a borrowed slice of bytes. But see that little tick A, that A? That is our explicit lifetime, and it's doing heavy lifting here. It guarantees to the compiler that the account view we're returning absolutely will not outlive the buffer itself. It's this rock-solid guarantee that we won't somehow end up with a pointer to memory that just doesn't exist anymore. So no heap allocations, zero cloning, just safe, read-only parsing that the compiler can verify in its sleep.
Section 3 already, taking full ownership, the handoff.
So what happens when just looking isn't enough? Sometimes you need the actual item, right? You need to keep it or modify its state permanently. That is where an owned value comes into play. It's defined as a state value, usually something small and copyable, that is transferred and persisted entirely on the stack. Think of it like this. Borrowing is kind of like lending your lawnmower to your neighbor for the weekend. Taking full ownership, that's selling them the lawnmower completely. They can do literally whatever they want with it, and you no longer have any say or any access to that lawnmower. The handoff is total. And that exact lawnmower logic translates perfectly into our Rust code right here. Look at the transfer value function. It takes v, which is a small value, completely by value. Notice there is no ampersand here, no borrow. The function just consumes the input entirely, taking full ownership. Inside, it can mutate it locally, maybe it's incrementing a token counter or updating a nonce, whatever you need, and then it returns a totally new, owned result. The caller loses ownership of the original data, and since we're dealing with small values, this whole operation is super cheap on the stack. Plus, the borrow checker is thrilled because the handoff is absolute. No messy overlapping claims.
Part 4, splitting mutable borrows, divide and conquer.
Now we are at the trickiest engineering challenge of the day. How in the world do we safely update two completely separate parts of a single data buffer without causing a massive memory collision? Enter our most ingenious tool yet, split at mute. By definition, it's a totally safe mechanism used to divide a single mutable slice into two completely non-overlapping mutable borrows. You know that normally our patent inspector strictly forbids having two mutable references to the exact same data at the same time, right? Gotta prevent those data races. While split at mute acts as an incredibly elegant engineering loophole, it mathematically proves to the compiler that our modifications literally cannot overlap. The structural logic here is just pristine. Step 1, we calculate and find the exact middle of our buffer. Step 2, we slice that buffer right down that dividing line, creating a distinct left and right slice that do not overlap by even a single byte. And finally, step 3, we can now mutate those regions completely independently.
because the compiler can mathematically guarantee that the boundaries of the left and right slices don't ever touch, it just gives us a green light to operate on both at the exact same time without throwing a single borrow checker error. And here is the exact syntax for that safe slice mutation. Let left, right equals buff.split@mute, passing in mid. I mean, it's incredibly clean. You can now iterate over the left side to, say, increment a set of values, while simultaneously iterating over the right side to decrement them. By actively avoiding those long-lived overlapping borrows, you're structuring your code in a way that the compiler implicitly trusts. It's just a brilliant way to handle state changes safely.
All right, our final section. Part 5, Testing Your Inventions, the Inspector's Checklist.
We've drafted some pretty incredible blueprints today, but now we actually have to prove they work flawlessly in the real world using cargo test. When we run our tests, this right here is the exact checklist the inspector is looking at. First bullet, the code compiles with 0 borrow checker errors. Obviously, that's baseline. Second, our assertions must actively validate the parsing and mutation logic, making sure our values behave exactly as expected at runtime. But pay really close attention to this third bullet, because it is vital. Comments explicitly stating ownership boundaries. Writing explicit memory comments directly into your code is practically mandatory. They document exactly who holds the buffer at any given time. In really complex programs, having small functions with clear boundaries and excellent comments is absolutely your best defense against those tangled borrow checker nightmares later on.
So, to tie this all together, here's a beautifully drafted cheat sheet summarizing the 3 main blueprints we looked at today. This tells you exactly which tool to grab off the workbench. Need read-only account parsing? Grab the borrowed view. That implies 0 allocations. Need state values that must be moved or persisted entirely? Use an owned small type, stored super cheaply on the stack. And if you need to mutate disjoint buffer regions safely, deploy split mutable borrows to keep those memory scopes distinctly separated. Okay, so we have thoroughly mastered individual memory boundaries today. You guys are pros at this now. But that leaves a very provocative, looming question. What actually happens when multiple counts collide? Like when we move beyond a single buffer and try to manage shared or concurrent access patterns across a bunch of different accounts? Well, that is exactly what we're going to tackle in our next lesson on debugging concurrency and unsafe patterns. Until then, just remember, keeping your memory usage explicit and intentional is your absolute best defense. Thank you so much for joining me for this explainer, brought to you by Forge College. If you want to dive even deeper into this subject and explore some more incredible Web3 topics, head on over to forge.college. Keep building those safe blueprints, keep learning, and I will see you in the next explainer.